All right, we're ready to get started here. Thank you for everyone who's attending the webinar today. I'm really excited. So this is our first core class in our soon-to-be completed Lagoon Masterclass, and today we're going to talk about wastewater lagoons and give you a really foundational overview of wastewater lagoon systems. So my name is Patrick Hill. I dubbed myself a PhD. Some people call me PhD, actually, believe it or not. But a PhD from Lagoon-university is what I would say. I'm one of the founders here at Triple Point. This is me on a boat doing some sludge measurement on a lagoon not too much more than a year ago. I've been working with lagoons for 16 years and have seen talked to a lot of people, seen a lot of lagoon systems over that 16-year period, and I'm really proud and honored that you're taking the time to spend with me today and learn what I know about lagoons so I can teach you a little bit. So today we're going to talk about wastewater basics, types of wastewater treatment facilities, lagoon systems in particular, and then kind of the disposal side of it as well. I'm trying to really not make any assumptions about what you do or do not know, and really start from the ground up and build this up. And that's how we want to do this masterclass. So, as I mentioned, we're putting together what we're calling a Lagoon Masterclass, and it's going to be about 12 hours of training within 6 different core areas of focus. The first is lagoon process, and this is going to be the first module in lagoon process. And then Brady, my colleague, is going to do another module, and we're going to build those out, and then we're going to build out all 12 hopefully over the next year and a half. And by the end, if you go through all the Lagoon Masterclass, and we'll have it up on our Lagoon-university site, you'll be a certified Lagoon Master, hopefully. Without further ado, I'm going to get started with this. So what is a lagoon system? So a lagoon system is kind of like a lake or a pond, and people call them ponds quite frequently. And really what it is it's a lake or a pond that you have an defined influent point and a defined effluent point in this lake or pond. And we're putting wastewater in, and we're allowing it to sit for a period of time, and then allowing it to flow out. On a very basic level, that's what a lagoon is. And the lagoon is relying upon microbial activity within it with the aid of algae, wind, and sunlight to break down the waste. They do take up a decent amount of space, and that's why they more generally are found in more rural communities. Lagoons have been around for a really long time. The ancient civilizations of Egypt and Greece and Rome all used lagoon systems in one form or another. And even it was used in the Middle Ages by monks, and abbeys used to have lagoons, their own lagoon treatment systems. And monks are pretty smart, because you know what monks also did is they also invented beer. So I put beer and lagoons in the same category in terms of awesome inventions. In the United States, the first lagoon was used in 1901. Recorded use was by a small settlement, and they became very popular in the 1960s after the Clean Water Act was passed as a wastewater treatment method that could be utilized in smaller communities in more rural areas and so on. And that'll be evident as to exactly why pretty soon. In the 2000s, so lagoons became very popular, and as in the 2000s, there was this sort of general perception going around that lagoons were outdated technology, that they couldn't treat the new nutrients that were starting to put limitations on wastewater treatment facilities, and that honestly they needed to be replaced by more mechanical systems that could meet the requirements of today. And over the last, I'd say 10, 15, maybe even 20 years, you could say, there's been a bit of a renaissance in terms of lagoons and actually upgrading lagoon facilities to help meet these new challenges, as opposed to replacing them, actually upgrading them. And so what we have seen is that a number of different manufacturers, including Triple Point, have been working on providing upgrade solutions for ammonia, phosphorus, and ultimately total nitrogen potentially. And this picture here shows you one facility in Missouri that we actually upgraded to help them meet an ammonia limit. And so that's becoming more and more popular and getting more and more traction. And you're starting to see that more and more. So there are a lot of lagoons. This is very significant in terms of the overall wastewater treatment composition. I was researching this again. I used to think that lagoons made up about 1/3 of all wastewater treatment facilities. Now they make up about 50%, is what I researched yesterday according to the EPA, and that's over 8,000 lagoons across the entire United States. And you know, you can see in this map, this is a map that we created and worked on that shows you all the lagoons and all the different locations. It's very significant. 60% of those lagoons are what's known as facultative lagoons, and we'll talk about what a facultative lagoon is here in a minute. But there are a lot of lagoons, and I'd say why this is important is that from an environmental standpoint, lagoons have a massive impact on the overall environment. And in particular, there is what's driving all these nutrient regulations is the dead zone off the Gulf of Mexico, which is essentially an area off the coast of Mexico, Gulf of Mexico, that is 6,000, almost 7,000 square miles in size, where there is so much nutrient pollution in that area that very, very little aquatic life can live. And when you think of lagoons at being, you know, 50% of the overall number of wastewater treatment facilities, a lot of these lagoons being in the Midwest, therefore a lot of these lagoons are in the Mississippi watershed, which flows down to the Gulf of Mexico. This is significant. Now you may be thinking to yourself, well, I don't care. I don't, you know, that's macro. That's too big for me. I don't really identify or understand that. Well, what I would say is for anybody who likes recreation, right? Anybody who likes to fish, anybody who likes the outdoors, anybody who likes, you know, just clean water in general, you know, this is a big deal. Like, you know, this nutrient pollution is harming those aquatic ecosystems. It's making them less useful to us, less beautiful, and so it makes a big difference. And this is why we focus on lagoon systems, and this is why we provide this training for lagoon systems, because we want to help lagoons do it better, and by doing so, help the overall environment. All right, so there's your context. Let's start from the top, or from the bottom as it might be. So where does wastewater come from? So really there's two main sources of, obviously, of wastewater. There's the domestic uses, things like human poop and pee, food scraps, fats, oil, and greases. And this kind of waste comes from homes, offices, schools, gas stations, restaurants, you name it. And it tends to be coming from, collected in a municipal system, right, through a collection system, which we'll talk about in a minute, and eventually finding its way to the plant. As you have this big collection system, one of the other sources of domestic flow is what's called infiltration and inflow, or I&I. And that is, and I'll explain a little bit in a second, but that is basically the intrusion of rainwater getting into the sewage collection system, is basically what it is. And that's a major, major source. Now, if you happen to live up in the Pacific Northwest, and you happen to use go to take a pee like these guys are in this picture, you may look down and see a urinal cake that says Brady on it. We like to make fun of this around here because sometimes when I get to go to Oregon or Washington State, I get to pee on my colleague Brady, which is fun. And if you don't know Brady and you don't want to pee on him, you can think of Tom Brady if you prefer. So we always crack that joke around here because it's kind of funny. The second source is industrial, and that's really wastewater that's coming from any kind of industrial scale kind of manufacturing. And so we do a lot of work with food processors, you know, sugar beet processors that are creating granulated sugar. With pulp and paper is something we're starting to work on now. Oil and gas, just any matter of industry. You know, you walk around a store, anything you consume is produced somewhere, and a lot of times those industries are producing wastewater, and that wastewater needs to be treated. Generally speaking, it's treated by the industry, but there are a lot of instances with lagoons where that industrial waste is getting mixed in with the municipal waste and going to the municipality to be treated. And so that's where it becomes of concern for municipal. It's usually a higher concentration of everything, BOD, ammonia, it'll be all across the board. There'll be some pretty crazy concentrations associated with this type of wastewater. So now the wastewater has been generated, how does it get to the plant, right? Where does it go from there? Well, you know, within a municipal setting, as this is showing, you have what's called a collection system. And really what it is you flush the toilet, right? All the water goes down a pipe, flows into a bigger pipe, which then flows by gravity downhill to a pump station. Sometimes this is also referred to as a lift station. And you have a vast network of a sewage collection system like this. And it all works on gravity until it gets to the lift station, and then it gets pumped out of there and pumped over to the wastewater treatment facility. They call it a lift station because oftentimes the pump is actually lifting the water. It's coming from a lower elevation, going to a higher elevation. Now, what happens with these systems, especially when you have big collection systems, is you get a problem called infiltration and inflow, or I&I. This is technical, well, it's sort of the short that everybody uses. And I&I occurs when you have, let's say, roots from trees that you know, basically intrude into the pipes. You can also see just broken pipes, old pipes, or pipe connections are very common. Over time, they deteriorate underground and they get leaky. Manholes can get cracks in them. Even sometimes you get what's called cross connections, where you have a stormwater pipe that is somehow getting cross connected with a sewer pipe accidentally. And all of this creates a massive inflow of water into these leaking systems that are leaking inwards during a rain event. And so you can see facilities that have triple, up to 10 times the amount of flow during a rain event versus during a normal dry weather day. And that's a big deal, and I'll explain why that's a big deal in a minute. So it gets to the plant. Now what happens? So what happens at wastewater treatment facilities and lagoons also is that the lagoon utilizes a biological process to break down the organic material. And it does this by fostering the growth of microorganisms. Now, in nature, this is just a very, very natural and innate process. Like, so if you take a banana peel, such as in this picture, and you throw it on the ground, and you walk away, and you leave, right? And you come back 2 weeks later, that banana peel's gone. What happened? Nobody picked it up, right? It was broken down by microorganisms. In some cases, it can be insects and ants and things like that too, but it decomposes, right, in place. And it's the same thing that we're trying to do in wastewater plants, except we're trying to do it in water itself, because that's where the organic material is. In order to do that, we utilize 2 different types of microorganisms. And, you know, in the industry, we call them bugs, you know, for short. It's kind of a fun thing to say. And you've got your heterotrophic bugs and you've got your autotrophic bugs, right? Your heterotrophic bugs are your primary workhorses. They're your terminators. They're the ones really consuming most of the organic material and doing so in a fast time period. And your autotrophic bugs are a little bit more fickle. They're like the princess and the pea, right? And they're typically used for nitrification, for example, which is a really, really critical step needed to get rid of total nitrogen. And so your BOD consuming bacteria are faster, They're stronger, they're less sensitive, they consume more, and then your nitrifiers are slower, weaker, less competitive, have very specific needs. They don't like to operate out of certain ranges of parameters, things like this. And these are the two workhorses that you see in wastewater plants that are really doing the treatment for you. So to give you a sense of how powerful these microbes are, if the earth, imagine the earth, okay, as a ball of cream cheese, right? Not cream cheese, cottage cheese. The whole entire earth is like one dripping ball of cottage cheese. And believe me, I tried to find a picture of a ball of cottage cheese floating in thin air and could not find it, so I settled on this bowl. But you get the point, okay? And let's say we dropped one bacteria on top of this ball, okay? How long would it take for that bacteria to consume the entire earth? I'll give you 5 seconds. Well, it turns out it would take about 72 hours for that one bacteria to eventually consume the entire earth, right? But what's happening is the bacteria is splitting, it's reproducing, it's growing. And so half the earth would actually be consumed in the final 60 minutes. That's crazy. Half the earth would be consumed within the final 60 minutes. And that is a testament to really the laws of exponential growth, right? Within these bacteria, one bacteria grows, it splits into two, those two split into two, those two split into two, and boom, 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 all the way along the line. And that's how powerful these microbes are when you harness them correctly. And that's what wastewater treatment's all about. It's all about harnessing the power of the microbes, giving them an environment in which they can thrive and do their job. It's as simple as that. Okay, so key parameters. So the first number one thing is biochemical oxygen demand. And really, this is a proxy for the amount of bugs that are there. So really what the measurement is in terms of a lab measurement is that they're measuring how much oxygen is consumed, how much the oxygen, dissolved oxygen in a sample of wastewater is reduced within a 5-day period, okay? And they basically use that to derive how much organic material, which is really coming from the fact that the bugs are consuming the organic material and consuming oxygen at the same time. So generally speaking, the lower the DO delta, the higher the BOD. And so it's really just a proxy for how much waste. And this doesn't just incorporate the organic material, this incorporates ammonia, because the ammonia bacteria, the autotrophs, are consuming ammonia. It incorporates, it's really a catch-all for a lot of things. The next one is total suspended solids, or TSS. And all this is you get a wastewater sample and you jam it through a 0.4 to 1.2 micron filter, okay? What stays on one side of the filter are the solids. What passes through to the other side is the water. And then they're basically cooking that filter, right, to boil off all the water. And then they're seeing how many solids that are suspended in the water column. So it's a measurement of mass is what it is. And some of that solid is BOD, some of that solid can be sand and grit and inorganic materials that find their way into the wastewater. It's really a grab bag depending on your type of wastewater, but that's all it is. It's the amount of solids that are in the water. Dissolved oxygen. Dissolved oxygen is a measurement of what it sounds like, dissolved oxygen. People also call it DO for short. When dissolved oxygen is low, it tends to lead, it can be kind of an indicator that BOD is really high, or that there isn't enough oxygen in the water to treat the BOD. Generally speaking, if you have over 1, it's considered aerobic, or that means you have sufficient oxygen to break down things with oxygen. If it's under 1, it's anoxic, which means you're getting a little bit of aerobic digestion, a little bit of anaerobic digestion. And then if it's less than 0.1, it's typically considered more anaerobic, which means you you're breaking down the waste. The bugs are breaking down the waste without oxygen. pH is a measure of how basic or acidic water is. 0 to 14 scale. 7 is neutral. 0 is acidic. 14 is alkaline. pH is important. The reason pH is important is because the bugs don't like extreme pHs. If you have a pH under 5 or over 10, right, you tend to get toxicity, and the bugs themselves don't operate in those toxic zones. Like, you won't get a colony of bacteria living in a vat full of acid, right? Makes sense. It can't grow in acid, right? And so you do need to pay attention to this as a wastewater operator and engineer to make sure more neutral the better, but it can operate within certain ranges around neutral. So total nitrogen. Total nitrogen is simply the sum of all forms of nitrogen together. That's why it's called total nitrogen. So what are the forms of nitrogen? You have ammonia, you have organic nitrogen, you have nitrite and nitrate. Okay, add them all together, you get total nitrogen. There's another thing called TKN, or total Kennedal nitrogen, which is basically just ammonia and organic nitrogen together. You'll see that a lot. Sometimes you see it on permits, sometimes you see it at labs, but TKN is just ammonia nitrogen plus organic nitrogen. In that case, total nitrogen is TKN plus nitrite plus nitrate. It's all the same thing, just a different way of calling it the same thing. Total phosphorus is similar. It's all the different forms of phosphorus together. It's tested that way. Phosphorus is a really, really important nutrient. It's one of the most important nutrients. It's used in fertilizers. Phosphorus and nitrates are big in fertilizers. It's super important for the growth of new bacteria. It's also super important for the growth of plants. So when phosphorus finds its way into the downstream environment, it tends to cause a lot of plant growth, and it tends to be a big driver of the dead zone off the Gulf of Mexico because of it. Finally, fecal coliform in E. coli. Fecal coliform in E. coli they really come from, they're microscopic organisms that come from our guts or animal guts, our stomachs, that is, and it can be found in feces, and they can be super, they can make you really sick, basically. They can kill you potentially. And so it's a really, really important metric. It's pretty much on every permit that I've seen. You see these kind of fecal coliform requirements or E. coli requirements, one of the two. And I mean, I know, like, for example, we work around wastewater lagoons all the time, and one of our guys a couple months ago was out in the field and got some wastewater in his mouth, I know, and was sick. In fact, I think 3 of them were sick for like a week. No doubt that was fecal coliform or E. coli that caused that. Okay, so flow and loading rates. So I'm going to use municipal because industrial is all over the map, but the point is exactly the same. In the 10 state standards, which is a standard which I will show you the reference to at the end, that basically all the engineers and regulators from 10 different states, mainly in the Midwest, came together and said, okay, we're all going to agree on certain things, right? On certain engineering things. And part of what they agree on is say, for every one person, we're going to assume that they produce 100 gallons of wastewater per day. So that's you going about your daily business. That's you going to the bathroom. That's you washing your hands. That's you washing the dishes, turning on your dishwasher, whatever, right? It's gonna be about 100 gallons per person per day. Truth is, that's a little high, but in the engineering world, we love to be conservative. So that's what we are. The second thing is that each person's going to produce about 0.17 pounds of BOD per day. So you're going to poop about 1.7. It's not all poop, but I'm going to use poop because it's easy and it's fun. Everybody loves poop. You're going to poop about 1.7 pounds per day. Third thing is you're going to produce a certain amount of TSS along with that, and a certain amount of TKN along with that. So to give you an example, if your population was 100, right, and that would mean your design flow is 10,000 gallons per day, and your loading to your wastewater system would be 17 pounds of poop, 20 pounds of solids, and 3.6 pounds of TKM. Now, what I think is really interesting about this when I read these numbers, and these are small numbers. I mean, we don't deal with these numbers very much. I just made them small to make them easy. That is, if you had 17 pounds of raw poop sitting in front of you, like let's say, like 100 people came and they all pooped in the same spot, okay? You had 17 pounds of poop. That's what your wastewater plant is receiving, okay? It's easy to think about it. Well, it's liquid, it's all mixed up with the liquid. You don't really see the physical amount of poop that is, but it's a pile, man. And your wastewater treatment plant's got to treat that, and it can go up from there. So I always find it really interesting to kind of visualize what that would look like right in front of on my desk, because that's what your system has to deal with. So now you figured out the flow. Another really important flow and loading, another really important metric is looking at the lagoon volume and how that relates to what's called hydraulic retention time. So hydraulic retention time is, in layman's terms, it's the amount of time that water nominally sits in your lagoon. So it's the average gallon of water coming in your lagoon will stay there for 3 days, 20 days, 25 days, 120 days, whatever that number is, right? That's what your hydraulic retention time is. So you calculate it by first figuring out what the lagoon volume is, right? And like anything, it's length times width times depth, right? In the case of lagoons, you have berms. The walls aren't straight, so you have to take out the volume of the berms. A whole bunch of math I'm not going to get into here. But that's what tells you what the HRT is, okay? And really all it is you take the basin volume divided by the gallons per day. And I'll explain, I got a few examples here. And so I want to circle back to why I&I is such a big deal. Infiltration and inflow is a big deal. The reason infiltration and inflow is a big deal is because when it rains, a lot of water will get into your collection system that will then flow to your wastewater treatment plant. This means that you could have a massive influx, okay, of additional water that you don't normally have. And you're going to see a reduction in your hydraulic retention time, okay? And this is very important from a treatment perspective, because those bugs, they need time to do their job. And if they don't get time to do their job, or they don't have enough time to do their job, you got a problem, because you're not going to meet permit. So let me give you some math and some examples here. Let's go back to the 10,000 gallons per day flow, okay? And you have a basin that's 250,000 gallons, okay? That's the total volume of your basin, okay? At that flow of 10,000 gallons per day, average flow, you would have 25 days of retention. That's good. Lagoons need retention, okay? That's great. Let's say your flow tripled because of a rain event, what we call peak daily flow. That's not your average daily flow, which is what you get on your average nice, beautiful summer day when everybody's chilling and nothing unusual is going on. This is your, it's raining, it's spring, it's fall, I got 30,000 gallons a day. Well, guess what? Your retention time went from 25 days to 8.33 days. So it went down significantly, right? Basically almost 3/4 it dropped, 75% drop. And that's a big deal, because your lagoon's gonna have a harder time treating that waste, right? Or any wastewater treatment system is gonna have a hard time treating that waste when it has 75% less time to do it. So here's another reason why this is a big deal. It's not just that the treatment time, right, gets reduced. It's also that if you, let's say you have a downstream treatment process, and that could be, I'm going to talk about nitrification here, but it could be disinfection. It could be some other downstream process. So this is a facility that we did It's a 3-cell lagoon system. And they put our nitrification reactor near the back of the plant to help a lagoon meet an ammonia limit. Okay, so this is one of those Renaissance upgrades that we're doing a lot of work on now. So you have Lagoon 1. This is taking obviously your primary flow from the lift station down here at the bottom. Lagoon 2, these are true treatment lagoons, pretty typical setup. And then it flows through the nitrification system and into the polishing cell. And then ultimately out through disinfection. So what happens is when they get a rain event at this lagoon, they get a massive spike in flow. Okay, their flow goes up. In this case, it's like 10 times or 11 times the amount of normal flow. It's a crazy number, okay? And here's the problem with it. It's not only just that they reduce the amount of hydraulic retention time, is that when water gets pushed, what happens is water comes into Lagoon 1 and it pushes water out of Lagoon 1 and it pushes water into Lagoon 2. And the water from Lagoon 2 gets pushed into the nitrification reactor. So it doesn't immediately get diluted by all the rainwater. It just pushes that flow and that loading with all that material through it such that you get a massive spike in the amount of actual pounds per day of ammonia going into that nitrification reactor. It got 102.7 pounds more ammonia within 48 hours. And guess what? Bugs don't like that very much. Bugs have a hard time with that, right? They'll catch up, they'll get it done, but they have a hard time with that. And that's why I&I is such a big deal. It not only reduces the amount of treatment time, but it's pushing loading quickly and quickly towards the back. Now, luckily, the regulators understand, right, these things. And so most permits, which we'll talk about permits later, will have a 30-day average. So you might theoretically in this day bust your permit for a day if you took a sample that day because of this instantaneous loading, pushing water backwards. But at the end of the day, you'll come back and if you measured took your samples every single day for a month, you'd be fine for the average basis. But it's still a very important thing to keep track of. So wastewater treatment. I'm going to talk about wastewater treatment. I'm going to talk about different types of wastewater treatment facilities. And then I'm going to talk about how lagoons do those things. And I think this is a really good context. There's really, every wastewater treatment facility really has, primary, secondary, and tertiary treatment on some level or some degree, typically. And there could be some variances, but this more or less covers the 3 main stages. Primary treatment is where you're trying to get some of the trash or screen out some of the trash or some of the things that came through, and then what we call grit. And grit is really sand, silt, anything that's heavy-ish, that's not biological and can't be broken down, right? Isn't organic, right? Sands, grit, concrete, whatever that might come through in the system. And then also in primary, if you have you have what's called primary clarification. So that's where you're using a screen to take out some of the debris and maybe some grit removal if you can, if you got that, if you're a mechanical plant. And then it's going into a clarifier and all the solids are settling down, right? And then that water is then sent to a biological treatment process. And that's where you're really trying to remove 85% of the organic matter within the incoming waste stream. And typically this is done with aeration. And you have the aeration and you're really trying to break down that. You also have what's called sludge digestion, which is, all that sludge that settles out. You want to potentially break that down over a longer period of time. Typically, they use anaerobic digestion in a more mechanical plant, but you're trying to deal with those waste solids that you can't necessarily treat quickly. Then finally, you have disinfection, nutrient removal, if you have a requirement, and any other polishing that might be needed. Sometimes there's a filter or something like that. So these are the 3 main stages, and each plant does these 3 stages a little bit differently, each type of facility. So this is your typical activated sludge plant. Right up here, you've got the screening facility. Then you have primary settling. This is where you're settling out some of the sludge. Then water will come down to the bioreactor. And this is just aeration tanks. And this is, all these aeration tanks are just full of just nice, dark, really dingy water. And the whole goal is you're trying to get the bugs to be as concentrated as possible and trying to get the food, the bugs, and the oxygen together within this aeration basin as best you can. So after it flows through the bioreactor, it actually goes into these clarifiers, and then solids settle down off the clarifiers, they're called secondary clarifiers, and then they take some of those solids and they actually put them back into the aeration basin. Why do they do that? Well, the reason they're doing that is because those solids have bugs in them, right? Those bugs are just floating around and the water looks all nasty, but really what is happening is it's being broken down, it's being cleaned, and it's going into the clarifier. They're settling out and they're sending it back. And so they're hyper concentrating the amount of bugs that are in these bioreactors in order to get the most efficient possible treatment they can. It's all about getting the bugs, the oxygen, and the food together. Anything that comes off the top of that clarifier, what they call a decant, which is just a fancy word for the water that's at the top, that where all the solids settle by gravity, all the clean water goes up, goes over, and then eventually goes out to disinfection, which is actually, where are we? Disinfection's on here, oh, right here, chlorine contact chamber. And that's where they get disinfection and then eventually ends up into the river. This is a very, very typical activated sludge type process. The other one is what's called an SBR or sequencing batch reactor. And this is a little bit different because instead of having clarifiers and different things like that, they rely on having more or less fewer basins or one or two basins, and they treat water in a batch basis. So you'll typically have screening coming in to take out any trash, sometimes grit removal, and then it will flow into a single tank, okay? And as the tank is filling up with water, right, eventually it fills up and it shuts off, and they have what's called an anoxic period. And this is really for treating for denitrification in a lot of cases, but you do get some BOD removal with this as well. And then it goes from an anoxic stage to an aerated stage where it's aerated. That means there's oxygen being added, you got complete mixed environment. Then the aeration shuts off, and they typically will have another kind of just mixed stage here. And there's lots of different ways to do this process, so this is just kind of generalized. And then at the end, they have it sit and they let all the solids settle, and then they pull that decant off the top. So really what you have here is you have a primary clarifier, aeration basin, and secondary clarifier all in one basin. So it's kind of cool. It's kind of a cool concept. Saves a little bit on the upfront capital in terms of having less basins and a little bit on space. So SBRs become very popular within mechanical treatment processes. Finally, I'm going to talk about oxidation ditches. Now, oxidation ditches are kind of a very popular thing with like smaller systems, and actually they're popular with industrial systems as well. You can have that primary screen on the front end, and then wastewater comes into a racetrack, what they call kind of a racetrack. And this literally is setting it around in a circle. And part of the advantage of this is that when you're moving the water around in a circle and it's being mixed and it's traveling, you get a lot of air, ambient air transfer of oxygen, and you also have mixers in there that are mixing it intermittently. So the power, you can rely a little bit more on Mother Nature in order to create the aeration as opposed to having diffusers from the bottom. It also, these tend to be a lot bigger, these types of systems. So they can kind of handle a little bit more of that I&I flow, which can be problematic for other systems due to the size and the volume of the basin. It flows from the reaction tank to the secondary clarifier. You settle out solids. Some of those solids go back into the basin. Some of those solids get wasted and eventually dried and dewatered and hauled off. And then whatever comes off the clarifier goes into disinfection and ultimately discharge, or any other polishing. I'd say the big thing with these oxidation ditches that people complain about with them is like a lot of concrete. Like these things they're built out of concrete, and their concrete is everywhere. and they're kind of a concrete contractor's dream in a lot of ways. But they are kind of cool systems. So the good thing about mechanical plants is they reliably treat nutrients. They do have a high treatment capacity and a small footprint, so you do tend to find them for bigger cities. They pretty much always use them. The downside is high capital costs, increased operational complexity, high maintenance, increased operator certification. And it's so funny because I was searching around for memes. Well, I wasn't searching for memes. I was searching for lagoon memes because I'm a lagoon geek. But I found this meme, which kind of I think sort of illustrates kind of the difference between mechanical plants and lagoon plants. You know, the look on your face when a lagoon operator says he's a wastewater operator, because mechanical plants require a lot more operator attention. There's a lot more moving parts. There's a little bit more technical knowledge you need to know. You got to maintain the bug population. You got to change recycle rates. You got to do all this stuff. And with lagoons, they're just far, far simpler. So you basically have like a fifer when it comes for lagoons. There's a 2-fer, 3-fer, 4-fer, 5-fer. I think it's a 5-fer. So this is your standard lagoon basin. As the water comes in, you can have screening. Sometimes there's a very basic bar screen for a lagoon, but sometimes they don't have it. And so the water's coming in, you have your initial screening, it's just by gravity. Any solids that are coming in that are big, trash or grit or whatever, just settle out within the first portion of the lagoon. And then subsequent portions of the lagoon, you have a clarifier, right? Primary and secondary clarifier in one, because everything is just still and stagnant. On the bottom, you have a anaerobic sludge digestion / sludge storage basin. All those solids settle down. They start to break down anaerobically over a very long period of time, like 20 years, right? And they just sit there. You got sludge storage and sludge digestion all in one. Then you have an anoxic zone, and finally an aerobic zone at the top. And that's where you've got wind action coming down, mixing water, adding oxygen to water, and so on. And let's not forget about disinfection. The disinfection, because lagoons are so big and because they have such a big surface area due to their size, these UV rays from the sun actually disinfect the lagoon water. So as a lagoon operator, you don't got much to do, man. Like, there is a need to do some things. I'm not saying you don't do anything, okay? But most of the work is done for you, and you don't have to spend a lot of time. There's not a lot of mechanical pieces of equipment that can be broken or need to be replaced or fixed or whatever, right? And so this is why we feel like lagoon systems are such a great type of wastewater treatment facility. One of the reasons. So what's the catch? Well, as I mentioned before, lagoons weren't initially designed for nutrient removal. And so if you want to do that, you have to put on bolt-on processes to do that, which does increase operator complication a little bit. Eventually, you know, the whole biosolids management strategy with the lagoon system is the solids sit there, okay? And you do need to remove them at some point, okay? At some point, you got to take the solids out. And sometimes municipalities forget that, and they leave the solids in there, and they don't budget to remove the solids, and then they become a major issue later on down the road, because you can't just store solids in lagoons forever, right? Lagoon hydraulics can be an issue. That's mainly where water doesn't flow through the lagoon in the way you want it to flow through the lagoon. Sometimes it takes a shortcut, goes from one location to another location. And then finally, algae can get a little out of control, especially if you have biosolids issues. So lagoons do it better because they have low construction costs, low maintenance, minimal operator certification, and you can treat now to these new nutrient standards if you have the equipment in place. Downside is you do have to manage sludge in the long term. You have to hire a contractor. It's going to cost you $1 million or a lot of money to remove all the sludge in your lagoon system, but you need a budget for that. It does require land. And if you do need to meet those nutrient limits, you have to upgrade your lagoon system. So quick, there was a study done by the University of Illinois. This is another reason, yet another reason why lagoons do better, that looked at different contaminants such as drugs, chemicals, human hormones, things that are finding their way into wastewater systems that are being studied now as how they impact the downstream environment, you know? And this University of Illinois researcher found that lagoons removed about 88 to 100% of these types of drugs, chemicals, and hormones that are being flushed down our toilets these days. And that's because of their massive retention time that's in lagoon systems. And so this is a really interesting fact that it could actually come back to, at some point, these types of contaminants may be regulated, and lagoons might be needed in order to accomplish that. So we got, we're gonna move on to the different types of lagoons, and I'm gonna move through this relatively quickly. At a very basic level, you've got several different types of lagoon systems, and this is not all of them by any means, but this is kind of encapsulates, I'd say, probably the majority of lagoons. And when you look at this graph here, what you're looking at is basically how fast the wastewater can be treated through a lagoon system, right? And what determines how fast wastewater can be treated through any wastewater treatment system is how good of a job that system does at getting the bugs and the food together, and the bugs, food, and the oxygen together, right? So this is where mixing and aeration come into play, and this is why there's so many different aeration systems that are out there, because this it makes a big difference if you can add air and mixing to how quick they can treat. So the first one is facultative. That's the slowest, all the way up to complete mixed return activated sludge, and I'll talk about a little bit about each. So facultative, going back to our upgrade facility. Facultative lagoons are basically lagoons that tend to be very large relative to their flow and relatively shallow. So you're looking at about a 3 to 5 foot depth. And what it's relying upon is a very long treatment time, about 120 days of treatment time within a facultative lagoon system. And the water comes in, you get oxygen transfer at the surface of the lagoon that helps to create a little bit of mixing, helps to add a little oxygen to the water, and you've got that anaerobic, anoxic, aerobic type of treatment across the whole system. And these are great. They're great systems because they don't require a lot of work. You don't have to maintain anything. The water just gets pumped into this lagoon. It sits there for 120 days, 90 to 120 days, and it flows out and it's clean for the most part. And that's one of the benefits of the system. The downsides are they take up a lot of land. If you don't have the land, then they're tough to deal with. And eventually you do need to remove sludge. And this is the biggest issue I see, and this is why we have a whole module on biosolids within the Lagoon Masterclass, a whole set of courses on it, is that biosolids do need to be managed at some point. And sometimes people forget because they don't have to do anything with the lagoon, and they start to think that they don't have to do anything with the lagoon, when in fact you do have to remove biosolids at some point. The next is partial mix, and this refers to kind of how it sounds. It's partially mixed. So you have some air in there typically. You don't have a ton of air in there, but you have a little bit. So you have zones that are aerated and zones that are not aerated. You don't have a high mixed environment, but you get better treatment out of it. So if you think about it it's about, I think it's over 2 times the speed of treatment versus a facultative lagoon. So if a facultative lagoon needs 120 days of hydraulic retention time, an aerated lagoon needs about 25 to 30 days. So significantly less time because of this air mixing input that you get with these systems. So a lot of aerated lagoons, the vast majority of aerated lagoons are what we call partial mix, and they look just like this. And this is actually a facility in Georgia that we upgraded. The third type, and this is actually our favorite, not our favorite, but kind of partly created by Triple Point, is what we call vigorous mix. So if you have partial mix on one end, you have complete mix on the other side, and the middle is what's called vigorous mix, which is not quite partial mix, not quite complete mix. And this is just a little bit more mixing. It can be really, really useful if you have an existing partial mix lagoon that you want to create more treatment capacity in, because you do get faster treatment with vigorous mix. And then finally, complete mix. This is a facility down in West Jackson County, Mississippi. It's a 7 MGD lagoon system that we upgraded. They created a complete mix zone on the back end of their primary lagoon, and this thing just rocks it. I mean, you can see the bubble patterns here. Like, it is bubbles everywhere. It is completely mixed. All the solids are in suspension here. You get very, very fast treatment through this particular zone because of the mixing. And so that's when you get the best and highest treatments with complete mix. The downsides of complete mix is you do need a lot of air. Like, it takes a lot of air to do this. It takes a lot of aerators to get complete mix. And so unless you have a specific footprint requirement or a need, you're probably better off not having complete mix, to be honest with you. And the last one is what's called a complete mix return activated sludge. So this is like an activated sludge plant. So in this particular facility, they have 2 clarifiers right in here, primary and secondary, right in here. So it's an activated sludge process that uses a complete mix lagoon as its aeration basin. So it's kind of a hybrid. And we've done this at a number of different locations, and it actually works extraordinarily well. One of the main benefits of this is that the lagoon has such a big volume, and the retention time, even though it's pretty short within a complete mix lagoon like this, it's still way longer than a typical aeration basin. And so you can handle a lot of I&I, you can handle a lot of extra flow, and the lagoon itself just equalizes that flow. In this particular example, they have a dairy that flows into this plant. It's an industrial dairy that flows into the municipal system that gets treated at this plant. And oftentimes they'll get massive dumps of dairy waste on their front doorstep, and it'll just come into the plant. It goes right into the lagoon. And what I've been told by the operator is, he's like, yeah, you know, we get this dump at like 4 a.m. and yeah, it looked like the DO dropped maybe about, 1 or 2 milligrams per liter, but then we were good, and that shows you how much it can absorb. So these are very popular for industrial wastewater treatment. There are other types of lagoons that are out there. There's aerobic, anoxic, polishing lagoons, rapid infiltration basin, flow equalization lagoons, storage lagoons. I'm not saying these are the only types, but I'm just giving you some examples of the types of ones that are out there. So let's talk about permits. So here's an example of a typical permit. So as an operator, you really want to pay attention to what's on your operating permit. The first thing you want to look at is, do you have a flow requirement? Oftentimes, lagoons are designed around an average daily flow, but you don't necessarily have a permit limit for flow, right? And that's partly because I&I can come in and it can be a big issue, right? Where it really skews the numbers because it makes it look like your flow for 2 days is 1 million gallons a day when your flow is like 200,000 gallons a day. So you typically don't see that. The next thing I look for is I also look at the sample frequency. Like, if you have to pull BOD, TSS, E. coli, ammonia, as you can see here, oil and grease, how often do you need to pull it? Once a month, twice a month, once a day, twice a day? Twice a day is unusual. You don't really see that with lagoons. But this is super, super important because you get to choose as an operator when you pull that sample. If they don't specify in the permit, you could choose any day of the week you want, any time of the day you want, and that's really important. I have a whole course on sampling, which I'll give later, but you choosing when is super important. The type of sample is also important. In a lot of cases, lagoons, you get grab samples. Grab samples are literally where you get a bottle and you pull a sample, and you put water in the bottle and you take it to the lab. Other samples you can get are what are called composite samples, where you have a sampler that pulls a little bit of water for 24 hours and puts it into a bottle, and you have to take that. The constituents, obviously really important. Do you have BOD? Do you have TSS? What are your limits for that? In this case, 30-30 is pretty typical here. You can see on the monthly average right in here. But they also have an ammonia limit on this permit, which is super important. Oil and grease, everything. The other thing you'll see on permits, sometimes you see a percentage of removal requirement. It'll say that you have to remove 85% of the BOD. This is, again, pretty tricky because of infiltration and inflow. If you have diluted wastewater coming in, you could have a hard time meeting this. Even though you meet your 30-30 limit for 30 BOD TSS, you may not meet the percentage of removal limit, and a lot of operators hate this requirement. Again, I have a whole section on sampling, which I will give soon. Finally, you've got it all treated, you meet permit, how does it get out the back door? So there's a couple of different things. This is one example here where you have a discharge point. Water flows into a river, stream, any kind of watershed, basically. You can see here, this is actually some effluent from one of our plants in Missouri. It looks beautiful, nice and clean, very, very well done. The other option that people have is what's called beneficial reuse. And this is becoming more and more popular, especially in the Western states where we're running into water shortages. And this is where you take the water out of the back of your plant and you can go right to land application if you're applying it onto non-food-based crops. Otherwise, you can treat it even to a higher standard and reclaim it and potentially use it in toilets, different things. There's different options that people use this water for. A lot of wastewater plants try to reclaim a lot of industrial facilities try to reclaim their wastewater in order to use it as processed water. And so these are the two main options that you typically see is either discharge or you try to reuse it. So running a little long here, some good resources. The EPA has a design guide for lagoons, or has basically a general design and operations of wastewater pond systems. It's a really good resource. If you're interested, just you can Google this. The other one is you can look at the 10 state standards. This is another really good resource. And the last one is looking at Steve Harris, our good friend, and he's recently been kind of out of commission, but he wrote this book called Wastewater Lagoon Troubleshooting. Great book. We reference this book all the time. I'm not sure if it's still in print. I've been meaning to maybe contact Steve and see if he can get it in print, or if he'd allow us to print it, because it's been a really great resource. I'd actually like another copy for myself. But this is a really, really good guide and where we get a lot of our information. So with that, I'll open the floor up to questions. I know we don't have much time here. Sorry, I ran a little long. This was a lot to cover in this 1 hour module, but please put your questions in the chat box and I will answer what I can in the few minutes we have left. So there's a question about what is the HRT for different types of wastewater lagoons. So if I take it from like the slowest to the fastest, for facultative lagoon systems, you typically see about a 90 to 100 day retention time, 120 potentially. Up in Canada, it might be 150. It's really dependent upon the temperature and the average seasonal temperatures. If it's cold, the lagoons are slower. For partial mixed lagoons, you typically see about 25 to 35 days of hydraulic retention time. So it means you can have a much smaller lagoon relative to the flow. For vigorous mix, maybe you cut that down by a third, you're 20 to 25 days. For complete mix, you can do 3 to 5 days. For complete mix return activated sludge, it could be a day, it could be 2 days. It just depends on how you want to design it. So the more mixing and aeration you put in, the faster the treatment, ultimately the smaller the lagoon needs to be. That's what it comes down to. I'm not familiar, somebody was asking about the time for the number of days you need for hydraulic retention time. It can vary state by state. Like I said, it's a lot, comes down to the temperature of the state. If you're down south, you probably need less time. If you're up north, you need more time, and that's because the bugs are slower when it's cold. It's just like anything else. When the water gets cold or we get cold, we move more slowly and the bugs move more slowly too. So that's kind of what drives that. I have a question here about what parameters typically push facultative lagoons to do mixing and aeration upgrades. Typically, you would look at what I've seen this happen where you're upgrading a lagoon to add aeration that was facultative, was previously was previously not aerated, is if you need to either meet a stricter BOD compliance requirement. So let's say a lot of facultative lagoons might get like a 40 or even up to a 60 milligrams per liter BOD effluent requirement, and now they need to meet a 30. Then you might add air to the lagoon in order to create mixing and increase the level of treatment. So that, or you want to treat more flow or loading. Let's say the community is getting bigger, or let's say the community is getting an industry coming in and they want to put flow into the system, then you need to upgrade because you have more organic load coming in. And that's when you would typically add air. Well, I have a question about what's the acceptable sludge depth for lagoons. The typical sludge depth, so it's usually, about 2 feet of sludge storage is what is designed at the beginning. Sometimes it can be a foot. Again, this is very state by state dependent. Some states are more conservative than others in terms of their design standards for lagoon systems. But typically it's 1 to 2 feet. I would say where I start to get alarmed is at that 2 foot mark. If you're at 36 inches of sludge, 3 feet, you could have problems. And what happens is that 36 inches of sludge is taking up volume, and what it means is that your lagoon can't hold as much water. And as you know, what we learned today is that if you can't hold as much water, then your hydraulic retention time goes down, right? If your hydraulic retention time goes down, that means you can't treat as much. And so your BOD effluent starts to suffer, right? Potentially your ammonia effluent as well. So the other thing is you get algae growth when you have more sludge because the sludge has nutrients in it. The algae love the nutrients. They love that phosphorus and nitrogen they can find in that sludge. You can get short circuiting. I've seen lagoons where sludge starts to create pathways for water, like valleys, peaks and valleys, where water will just follow along these peaks and valleys through the lagoon. You can get all sorts of problems. I'd say the biggest issue with lagoons is sludge and being able to deal with the sludge adequately. If you can take care of the sludge and you can manage your sludge well, lagoons are slam dunk, hands down, best freaking wastewater system in the world. If you don't manage your sludge, slam dunk, hands down, worst wastewater system in the world. It really does hinge upon, well, I wouldn't say that, but maybe it's extreme, but sludge is very, very important to lagoon management. Somebody's asking about grass carp. I did a whole webinar on lagoon pests, and I dealt with grass carp in there. If you want to go to lagoonuniversity.com or go to our website, lagoons.com, and look at the resources tab to get to Lagoon University, look for the lagoon pests one. It deals with that in a little bit more detail, and I have time here. Could an operator RAS all the sludge? So what happens if you do have a clarifier or some means of allowing sludge to settle and you can have recirculate it back into the lagoon? What happens with that sludge is you're returning the sludge back into the lagoon. The benefit to returning the sludge back in the lagoon is you're concentrating the bacteria, right? You're adding more, you're sending it back, right, into the lagoon, and you're growing more, and you're adding it back, and growing more, and adding it back. And so you get faster treatment that way because you got more bugs, right? Makes sense. You do have to waste at some point, which means you can't just keep going around in a circle for infinity for a number of reasons. Number one, the bugs are only going to grow on the basis of the amount of food that's available to them. So as soon as those bugs ate the whole entire earth that was made out of cottage cheese, they all died because there was no food for them left, right? The earth was gone, right? And so if you don't have the food for the bugs are just going to die, right? And you need to waste those dead bugs ultimately. Secondly, the solids will just build up and build up and build up because you've got new solids coming in from the influent collection system all the time. And if you're just circulating over and over and over and over and over again, eventually you're going to have so many solids in the system because you're not getting rid of the solids. Like you're breaking them down, sure, but there's some solids you're not going to be able to break down. And you eventually at some point you got to waste, otherwise you're going to have too many solids in your lagoon. Your aeration system is not going to be able to mix it adequately because the water is going to be so thick with solids, and those solids aren't going to be doing anything for you because they're just dead spent bugs, basically. So you do need to waste at some point. And I'm not an expert at activated sludge. I'm really not. Like we do this a little bit, you know, we do activated sludge systems, but it's not something we do every day. We do it 1 or 2, 3, 4 times a year. And I have our process engineer who's a lot more versed in it. So any other questions we'll answer offline. We're getting almost 10 past the hour here. Thank you so much for coming today. I really appreciate it. We had 175 people on this call. That might be a record for us. I hope you enjoyed it. I hope I did a good job. Please fill out the survey and let me know how I did here. And I look forward to future webinars. And it's always just an honor and privilege that everyone spends time with me or time on these webinars, because I really do take them seriously. So appreciate it. Thank you very much. And I will let you go.